Okay. Hello, everyone. So, today is our last lecture, and I know that in syllabus were expected to solve the practice exam, but I want to use this last lecture to introduce you the concept of paging, which is kind of crucial. Uh, but here is the thing. The material which we are covering today, the last day, it will not be, you will not be responsible for it in the final exam because it's kind of unfair to like introduce you to the topic on the like last lecture day and then ask you to master it within couple of days, right? But still, I want you to at least understand it and know the basic things about paging, so that it can at least give you a pointer or a reference point for your further reading, or in future, if you come across this topic, you know what it is and what is the motivation behind having paging, right? But again, you will not be responsible for the material which we covered today in your final exam. Uh, about practice exam, what I will do is that I will release the practice exam and its solution. I will share it on the canvas and you can solve it on your own. And then, as I said, I will provide the solution. You can compare, you can first solve it and then compare it against the provided solution, right? And if still you have some question, then you can send me an email. Okay. Or if you want, I will also be available to do Zoom meeting if you need one. Okay. So, having said that, now let's move to our lecture today. So, remember last time what we were talking about? We said that in modern systems, we want multiple processes to run at the same time. So, which means that we want to load multiple processes in the memory at the same time. Definitely, it requires sharing the memory, or not sharing the memory in the sense that uh, memory is partitioned into different chunks, and then uh, let me switch off my cam because I think today my internet connection is not correct, not stable, so I should stop. I should switch off my cam. So yeah,
No problem.
so if we have multiple processes, if we want to run multiple processes, all of them need to reside in the memory, right? So it's mean that whenever the operating system loads the executable file of a program from the disk into the memory, it need to first find that if is there available or free memory space where I can put this program in the memory. Uh, and it means that also it needs to keep track of like which sections of the memory are already occupied and which sections are free, right? So so one option to handle this situation or to handle this problem of allocating the memory is known as the contiguous allocation. So in contiguous allocation, what you do is that when you load the executable file of a executable file from disk into the memory, you just look at the size of the file. And let's say if the size of file is, I'm just making up a number, 8 kilobyte, then the operating system will look in the memory and find a contiguous chunk of 8 kilobyte which is not allocated to any other already running process or already loaded process, and then this 8 kilobyte will be allocated to the newly loaded process. Similarly, if in future another process comes in, then depending upon its size, the operating system will look that, okay, which in the within the memory space where I can find a memory chunk which can accommodate this new process and allocate that memory to the newer process and so on, right? So, so the main point of contiguous allocation is that the 8 kilobyte or 4 kilobyte or 16 kilobyte, whatever size of the process is, you need to allocate a memory chunk which is contiguous. Like it starts from, let's say, from 4 kilobyte, and if the size of the process is 8, so it should go from 4 kilobyte up to 4 plus 8 is 12 kilobyte, right, in the memory space. So what you do is that main memory is partitioned usually into two partitions. One where you look at where you hold the resident operating system, and the other where you load the user level processes. Actually, we covered this slide in the previous lecture, but again, I just wanted to go through them quickly to set up the context for this slide here. So again, as we have multiple processes, so we need to have multiple partition allocations. And each partition of the memory chunk is the size of each partition is dependent upon the size of the process which we want to, or size of the program which we want to load in the memory. And once loaded, we refer to it as a process, right? So each partition contains a program or is free. So if partition is a free, it doesn't hold any program. So we refer to it as a whole. For example, if you look at this figure, let's say initially on the left side, this is the current snapshot of our memory. So the topmost section is occupied by OS, and then next we have a memory chunk which holds or into which we have loaded the process 5. Then in the next largest chunk we have loaded process 8, and the next we have loaded the process 2. And maybe after some time our process 8 has completed the execution, and now the memory is not needed anymore because the process is completed, so that memory is reclaimed. So it is marked as free memory or free memory chunk, and process 5, 2, and operating system continues running. And then maybe at some point in future, another process 9 is loaded into the memory, so it will be allocated a chunk from the whole. So the size of whole has now reduced because a part of the whole is now allocated to the process 9. So that whole is indicated here as the blue chunk of the memory. And then maybe again in future, let's say the process 9 has completed its execution, and but before process 9 has completed execution, process 10 is loaded into and it is allocated memory from that whole. And then while process 10 is running, process 9 completes execution and it releases the memory. So now we have two holes which are not contiguous, right? So as a like result of this how to say uh, this pattern where processes are allocated the memory when they are loaded, and once they are done the execution with the execution they are completed, the memory is reclaimed. We can end up in a situation where we can have contiguous memory, but we can end up in a situation where we have scattered holes. Like let's say we have a 4 kilobyte hole here and an 8 kilobyte hole here, but these are both of them are empty, but they are not contiguous, right? So what operating system need to do is to manage the contiguous allocation is that it maintains the information about allocated memory partitions in PCBs. So in each process control block, you maintain the information that how much memory is allocated for running a given process. And it also need to maintain a list of the free partitions, a list of the free holes, right? So free partitions are referred to as holes. As I said, when a process arrives, it is allocated memory from a hole which is large enough to accommodate it. Now the question is that how can we satisfy a request? Let's say we have a request by process uh, for the memory, and the size of the memory required by the process is n, and we have a list of free holes, right? Now, how can we satisfy that request? So this is actually a dynamic storage allocation problem, and where there are various strategies which we can follow to allocate or to serve the request of size n. So the first one is first fit. So this allocation strategy actually says that uh, you search the list of the free holes and you allocate the first hole that is big enough to hold the request. So like let's say if you have uh, uh, a chain of holes or list of holes, and in that chain the first hole is of size 4 kilobyte, next one is 8 kilobyte, next one is 12 kilobyte, so on. In this example I'm assuming they are ordered, but normally they are not, right? So let's say it is let me give you an example of unordered, right? Let's say it is 4, 12, and 8, right? So and your request of the process is let's say 8. So the first hole, which is of size 4, doesn't satisfy the request. The next one, 12, it satisfies the request, though it is much bigger than what you require, right? So but first fit approach strategy says that When you find the first hole which is big enough to accommodate the request or to satisfy the request, you allocate that hole, right? Next fit strategy, it says that it is same as first fit, but the difference is that when you try to serve a new request, you continue searching the list of free holes from the same point onward where you left in the previous search. Uh, let me let me quickly explain on one note. In the two. So what we are saying is like, let's say you have mm, memory, right? And in this memory, you have, so this one is, let's say, occupied. Then next chunk is free. And then the next chunk is again occupied. Next one is free. Next is occupied, and so on, right? So let's say this is 4 kilobyte. This is 12 kilobyte. This is 10 KB. This is also 4 kilobyte. So first, and let's say you have a request of request size is, let's say, uh, 8 kilobyte, right? So the first fit, FF says that you will searching. Does first hole can the first hole accommodate the request? No. Next one, yes. So you stop here and you allocate the first hole. The whole 12 KB chunk is used to satisfy our request, which actually needs only 8 kilobyte. So now this hole is occupied, right? So this is first fit. Next fit is like when you have another request. So let's say this was request one. So now when you have another request two, and its size is, let's say, 4 kilobyte. So you will not start searching here. You will start searching from onward from this point, right? So the next one is 10 kilobyte. So it can accommodate 4K. So you will allocate this one, right? So, but here keep in mind that here we needed 8 KB, but we used a whole of 12 kilobytes. So how much we are wasting? We are wasting 4 kilobyte here. And similarly here, we have a whole of 10 kilobyte and we use it to accommodate a request of 4 kilobytes. So we wasted 6 kilobyte, right? The next one is best fit. So best fit is that you allocate the smallest hole that is big enough, and for that you must search the entire list unless ordered by size. So here what you do is like, let me go back to one node. So for example, here for example we had let's say we have 8 kilobyte, right? 8 kilobyte is the request size. And let's say we start from the same time point where we have uh, 12 kilobyte hole here and we have 10 kilobyte here, right? So what you do is like you don't it is not the first fit or next fit. It is named as best fit, which basically mean that you will look for a hole which is small enough to hold your request, right? So can we hold 8 kilobyte request in 4 kilobyte? No. So can we hold 8 kilobyte request? Can we serve 8 kilobyte request by using a whole of 12 kilobyte? Yes, but we are not sure. Maybe if we continue searching, we end up finding a hole which is of exact 8 kilobyte size. So let's not stop here and continue. So next we have a whole of 10 kilobyte. Yes, it can also serve 8 kilobyte request, but we are not sure. Maybe if we continue searching, we will find another hole. Next, we find 4 kilobyte. which is smaller. So now we are done with searching the whole list, right? And the smallest hole which we find that is capable of serving the request is 10 kilobyte. So we use this 10 kilobyte hole to serve the request. Now you can see that it is better the first fit as the next fit. Why? Because it wastes the smallest space. For example, when we are using the first fit, how much bytes we were wasting? We were wasting 4 kilobyte. But now using the best fit, we are using a hole of size 10 kilobyte to serve a request of 8 kilobyte. So how much we are wasting? 10 minus 2, 10 minus 8, we are wasting 2 kilobytes. So this is better, right? As compared to first fit or next fit. However, the problem with best fit is that you need to search the whole list of the free holes to find the one which is small enough, smallest, which is smallest to accommodate the request. But in case of first fit or the next fit, you don't need to search the whole list. So there is like, trade-off. In first fit and the next fit, you don't need to search the whole list of the free holes. But in the best fit, you need to search the whole list, but you end up you use the space more efficiently. You don't waste the space as much as you would do it in the case of best fit and the next fit. So this allocates the smallest hole that is big enough, must search entire list unless ordered by the size, and it produces the smallest leftover hole. The next strategy is worst fit. Worst fit, you allocate the largest hole, must, and here you also must search entire list. This strategy looks a little bit counterproductive, because what you are doing is that you are allocating the largest hole. Like for example, if your request size is 4 kilobyte and the largest free hole is, let's say, 12 kilobyte, and there are also other like 8 and 10, so you will allocate the whole of 12 kilobyte. uh, but this produces the largest leftover hole, and the hope is that in future you will have other requests of smaller size which will be then placed in those leftover holes. Now, as you have seen, or maybe as you have now sensed it from these examples, that when you are serving the request, you may end up creating fragmentation. So, what is meant by that? By creating the fragmentation? Let me explain it using the figure in the next slide. So, for example, let me first explain the figure and then I can read the text. So let's say you again have the same situation, right? Where you have like process 8 and then process 8 is done. So it creates a hole when the memory is freed. And then you load the process 9, then process 10, and after some time, process 9 is done with the execution. And now you have two different holes, right? Uh, Let me select a pointer. So let's say that after this step, you load the process 3, right? And but it creates a very small hole, which I tried to show here as like the in the red color. And then you also load the process 12, and this also creates another hole, which I tried to show in the red color. The problem now is that maybe these red color holes are too small to accommodate a future request, right? For example, let's say this hole is, let's say, only 64 bytes, and this next hole is, let's say, only 100 bytes, right? So they are too small to accommodate, let's say, a future request by a process. But when you have lot of these small holes, and then if you combine their space together, then the total space is large enough to serve the request. But since these holes are not contiguous, they are not next to each other, they cannot be used. Remember, we are doing the contiguous allocation, right? It is required that the memory which is allocated to a process is contiguous in the memory space, right? But we have a large number of holes. Each one of them is small in size. Each one of them cannot individually accommodate a request, but when their sizes are combined together, we get a total memory space which is large enough to hold a future request. So now there is a dilemma, right? We have space available, but we cannot use it because to accommodate a future request because that memory space is not contiguous. So this is known as fragmentation. So contiguous allocation causes external fragmentation. So again, fragmentation can be of two type, external and internal. The one which I have shown you here is known as the external fragmentation. Uh, it will become clear to you why we name it as external when we'll talk about the internal fragmentation. So, but for the time being, the thing what happens is that we have small holes scattered all over, and individually they cannot serve any request, or they cannot fulfill the memory requirement of any future process. The total memory space exists to satisfy a request, but it is not contiguous. Now, what is internal fragmentation? So in some cases, what we do is like in some memory allocation strategies, what we do is that uh, the total available space that we have initially, which is available for loading the user processes, we partition it into uh, a set of equal size chunks. So for example, let's say uh, we first load the OS and then this blue color actually shows the free memory space. So let's say we partition the memory into two sets. In the first set, we have two chunks of 4 kilobyte, and in the second set we have also two chunks but of each of size 8 kilobyte, right? So now what we do is, unlike the previous example, what we do this time is that whenever we have a request, uh, we serve that request uh, from the appropriate set. Like for example, if you have a request by a process which is of size 4 kilobyte, you allocate it a chunk from set 1. Let's say, let me give them name for easy referencing, set 1 and set 2. Okay. If you have a request by a process at the memory size of 4 kilobyte or less than 4 kilobyte, so you will you will assign it a chunk from the set S1, right? So as shown here in this example. So process A gets a chunk from set 1. Now let's say then after that we get a request for process B, which requests a memory of size 8 kilobyte. So we allocated the chunk from the set S2, right? Now after that, let's say we have another request for process C. I should have given it name process C, right? And its request memory size is 7.9 kilobyte, right? So what we do is that we will allocate it the chunk from the S2, right? But here 0.1 kilobyte is wasted. The main difference from the previous example is, the previous strategy is that here we are allocating the memory in granularity of fixed size chunks. You can allocate the memory either in size of 4 kilobyte or 8 kilobyte, right? There is no uh, option of, like, for example, you cannot serve a request of 12 kilobyte, although you have, for example, at this time point you have the total space of how much, it's 1620 kilobyte, but you cannot serve a request of 16 kilobyte because you don't have a fixed size chunk of 16 kilobyte, right? That's the difference. But in the previous strategy, if you have total available space of 20 kilobyte and there is a request of 16 kilobyte, you can serve it, right? Okay, so here when we get the request of 7.9 kilobyte, we allocate this whole chunk of 8 kilobyte. Now 0.1 kilobyte is effectively wasted because the request size was 7.9 kilobyte. So that's why, since the memory that is wasted is within the chunk boundary or within the chunk size, it is internal to the chunk. That's why it is known as internal fragmentation. The external fragmentation was where you don't initially where you are not dividing the memory into equal size chunks or set of chunks, right? So you have a huge chunk initially, and whenever you get a request, you look at whether the I can serve the request depending upon the availability of the hole, size of the hole. If yes, you serve it and you create a new hole. So these holes are like not internal to a fixed size chunk. That's why we name them as external fragmentation. Okay. So, so what we have seen until this point is that if you are doing the contiguous allocation, there are two ways. One way is where you don't, where you are initially not dividing the free memory into equal size chunks. And in that case, you end up having fragmentation referred to as external fragmentation. In the second case of contiguous allocation, you divide the initial free memory into equal size chunks, a sets of equal size chunks, and then you allocate the memory in granularity of uh, those chunks, right? And in this case, you end up having internal fragmentation. Okay, someone has a question. If a process was already say 12 kilobyte in fragmentation, does it need to convert pieces, or would it just not be possible to work if the memory couldn't reach 12 kilobyte? Let me know if I understood your question correctly. You are saying that if a request comes in for loading a process, and the memory requirement of the process is 12 kilobyte, and the total memory that is available is 12 kilobyte in the memory, but it is not contiguous. Like it is in that chunk, those available holes are not next to each other. So in this case, you are saying that do we need to break the process into smaller pieces, or can we simply not accept the request and reject? Yeah, okay. So there is no such thing like breaking the process. We cannot break the process. However, uh, and under the contiguous allocation, if we don't have the contiguous piece of memory to serve the request, we will simply reject the request. We cannot allow that process to load. That process cannot be loaded. We can put it on wait until a contiguous chunk of 12 kilobyte become available. However, there is another approach where what we do, because remember, what is the restriction in the contiguous allocation? That the required size of the memory, it should be available in your memory space in a continuous fashion, right? So, for example, if you are, as I just said earlier, let's say you have a one hole. For example, we can use this one like 4 kilobyte and 8 kilobyte. Together, it is 12. But these but they are not next to each other. So you cannot serve a process which has a request of 12 kilobyte, right? So you will simply either reject the request, or you will ask the process to wait until, let's say, uh, this process is done and it releases the memory, and then you can serve it. But again, here uh, we are using the fixed size chunks, 4 kilobyte and 8 kilobyte. So maybe it is not a good example. But in this case, where you are not initially dividing the memory into fixed size chunks. If you now you have, let's say, if this hole is 4 kilobyte and this is 8 kilobyte, and now if you have a request or 12 kilobyte, you will not be able to serve it. You will either ask the process to wait, or you will simply reject it, send an error. Okay. However, there is a different solution which doesn't follow the rule or the restriction of the contiguous allocation. In contiguous allocation, we are saying that memory must be next to each other. The free memory holes must be contiguous or next to each other. The next approach which we see, it releases or it removes that restriction. It doesn't require the memory to be a free memory to be next to each other, as long as you have a total memory which can actually serve the request, or then you can allocate the memory. For example, uh, if here like 4 and 8, they are not contiguous. So, but in total, the capacity is 12. So you will say, okay, I can serve the request. How? We will see it in a minute. So actually, this is the problem what we are going to address using paging. So how can we handle the memory fragmentation? So you reduce the external fragmentation by compaction. What is compaction? In the compaction, what you do is that you move around the processes such that you bring the holes next to each other. So you shuffle the memory contents to place all free memory together in one large block, right? So for example, here, let's say you have initially you have like process 5, 3, 10, 12, and 2 running, right? And then you have these two small holes, right? And there is a request for process 6. So these two holes together can satisfy the request by the process 6, but since they are not contiguous, you cannot allocate the memory to process 6. So then what you do is that you simply move or shuffle the content of the processes in the memory. So for process 2 remains here, 12 remains at its place, but you move down a copy over the content of the process 10 in the memory, like move its content downward or copy them downward. Then process 3 is also moved downward. Process 5 is moved downward. Then here, and these two holes are moved here. This hole is moved here. This is also moved here, and together they are able to satisfy the process 6, the memory requirement of process. So this is known as compaction. So what you do is that you simply move holes next to each other by moving all the processes next to each other in the memory on one side of the memory. Other option is to reduce the external fragmentation is paging. So what is that? That you allow but here you are following the restriction that the memory which you are allocating is contiguous. The only thing you do is that to make those holes contiguous to each other, you move the content of the processes in the memory so that the free memory is next to each other, right? But you are following the restriction of like having a contiguous free memory space. In paging, what you do is that you remove that restriction altogether, requirement that the free memory should be contiguous. So what you do is that you allow non-contiguous memory to a process. So those holes, they remain at their place, right? So what you do is that when process 6 comes in, so you allocate both of these holes to process 6, but then you need to somehow track that both of these two holes are not contiguous and they are both of them are allocated to process 6, right? Now the problem with compaction is that you need to move holes next to each other, and for that it's mean you need to copy over the content of the processes in memory from one location to another. So for example, when you are moving process 10 down, it's mean you are copying all the content from this memory region to this memory region, right? And similarly, you are copying all the content of process 3 from this memory region to this memory region here. And process 5 also same. So they are all of them, content of all these three processes need to be moved. So it takes time, right? So which makes everything slow. So paging, it solves the problem of external fragmentation, and it also don't need to pay the cost of copying or moving over the content of the processes in memory. So process 5, 3, 10, 12, and 2, they stay in their place. The process 6, which is sending the new request or creating the new request, we allocated the holes, but we just need to track that those holes are not contiguous, and we need to maintain the information that those holes are allocated to process 6. Any questions? So that is just like introducing you to the very abstract concept of paging. The paging is a much larger subject. Uh, So here is how paging works. We will have examples in upcoming slides, so it will become more clear to you. So in paging, the physical address space of a process can be non-contiguous. It is not possible in contiguous allocation to have non-contiguous physical address space, but in paging, we allow processes to have non-contiguous address space. So process is allocated physical memory wherever the letter is available. Wherever you have the holes available, you use them to satisfy the request. What you do is that in paging, what is like how paging work, what is the working principle of paging? You divide the physical, remember, again, we have logical memory and we have physical memory. Like we have logical addresses and we have the physical addresses. So physical addresses, they are used to access the physical memory, which is the actual memory chip. Logical addresses, they only make the logical address space. They are not used to like access the actual memory, but these are just numbers. Like for example, if you remember from our previous lecture, we said like if let's say if you have I don't know, let's say if you have a 4-bit address space, you will have a logical address in the range of 0 to 15, right? But the physical address, it can be different. Okay, there's some comment. Is higher risk of memory overflow with paging, or is that a completely separate topic? What do you mean by memory overflow? You mean like we don't have the capacity available to serve any future request? Can you please elaborate? You can unmute yourself if you want to talk.
Yeah, sorry. So like is there a way that it like I know there's like buffer overflow errors. I'm assuming there's similar to like memory, but I'm not sure. Like with paging, since it's trying to fit, let's say, in such small spaces sometimes, is there a chance that there will be like an error within the OS at all? Or is there like, I'm assuming there's higher end checks to make sure that something like that doesn't happen? I assume like trying to put a process in that doesn't fit within multiple pages.
Okay. So uh, I'm just trying to refine or rephrase your question. So you are saying, uh, can there be a situation where a process uh, cannot fit into available number of pages? So let's say available number of pages are 4, and a process needs, let's say, 6 pages.
Yeah.
So okay. So actually, the paging is basically designed to handle this kind of problem, right? So basically, you are saying that the total memory requirement of a process is, let's say one page is 4 kilobyte. So you are saying that total requirement is 5 pages, so which means 520 kilobytes, right? And available pages are, let's say in the memory are 4 kilobyte. Free pages, 4 kilobyte pages are 4. So we are one less, right? So you are saying, can in this situation we can accommodate the process request or not? So under paging, yes, we can still run that process. But if we are using the contiguous allocation, we cannot. How we can still run it under the paging, I will explain.
Yeah. Thank you.
Okay. So what we do is, where was I? I was explaining that we have physical addresses and logical addresses. Physical addresses are used to access your actual physical memory or the memory chip. Logical addresses, they make uh, they make a logical memory address space, but they are not used to access the physical memory chip, right? Because we translate them first into physical addresses and then we use them to access the physical memory, right? So what we do is that under paging, that we divide the physical memory into fixed size blocks and we call them as frame, right? And and the size of the frames, they are typically in power of 2, like for example 4096, which is equal to 4 kilobyte. Okay, so 4 kilobyte is definitely 2 raised to power 12 bytes. Similarly, we also divide the logical memory into blocks of same sizes, and we call those blocks as pages. So physical memory is divided into blocks. Logical memory is also divided into the blocks. Blocks of both like physical memory and logical memory are of the same size, but we refer to them using different names. Blocks of physical memory, they are referred as frames, and blocks of the logical memory, they are referred as pages, right? Uh, now, we also need to keep track of all free frames of the physical memory. And by we, I mean the operating system keeps the track of all free frames of the physical memory. So to run a program of size n pages, so remember previously we were saying that whenever we want to run a program, we need to first allocate it a contiguous memory chunk. So let's, for example, if a program is of size 16 kilobyte, right? So it's mean that we can now divide uh, its memory requirement into pages. So if 16 kilobyte and each page is 4 kilobytes, so we will have the memory requirement of 4 pages, right? So to run a program of size n, or let's say in my case, in our example, 4 pages, we need to find 4 free frames and load the program, right? What is, remember, again, that we define the size of a program in terms of like logical address space. And we divide the logical address space or logical memory into pages. So if logical memory requirement is 16 kilobytes, that means 4 pages. But then we also need, we can again we convert the logical address, each logical address into a physical address, right? So it's mean that we need to translate each logical page into the physical frame. We need to put each if we have, if the requirement is 4 pages, it's mean we also need 4 free frames in the physical memory. So we then set up a page table which actually translate the logical addresses to the physical addresses. And this scheme can also have internal fragmentation. How I will explain. Let's first try to have a look at some example. Okay. Again, as I said, it is not, you're not responsible for this in your exam, but please, if you have questions and if you are not clear, stop me and ask questions and clarify the things. Okay. So how paging works? So let's say you have a program, right? So what you do is that you divide the logical address space of the program into pages. So what do you mean? Do you mean by logical address space? So for example, if let's say I have a program which is of size uh, 4 kilobyte. What does it mean that the program is of size 4 kilobyte? It's mean that this program, you have written the instructions, and when you convert it into, like, let's say assembly, then all of those instructions together, they occupy 4 kilobytes in the memory, right? So that's why we say that its size is 4 kilobyte. So if all of those instructions together occupy 4 kilobyte, so it's mean that at address 0 you will have an instruction, right? And let's say if each, I'm just like keeping it simple. If each instruction is of 4 bytes in size, the next instruction will be at the address 4, right? So the third instruction will be at address 4, 5, 6, 7, 8, right? 8. And the next one will be at 12 and so on, right? So the last instruction will be, you can do the math, 4096 minus 4. So it will be 4092, right? The next last instruction will be at the address 4092. So this will be your address range, right? Logical address space, right? Now, on the other hand, you have RAM, which is your physical memory chip, right? So you divide the physical memory chip into equal size blocks as shown here, right? And also, and you simply number them like block number 0, block number 1, block 2, block 3 up to block 9, right? But this is physical memory, which means that here you have address 0, and then it depends what is the size of this block. So let's say, okay, let me not confuse you. Okay, let me give you a simple example. Let's say that each block is consisted of size of 10 bytes, right? So 0 to 9 will be in the first block, addresses 0 to 9 will be in the first block, 10 to 19 will be in the next second block, and then like 20 to 29 will be in the third block and so on, right? Okay. So each of this frame is known as a frame, is referred to as a frame. and typically its size is power of 2. And in most system, by default, the frame size is 4 kilobyte, right? So physical memory, set of fixed size frames. So you divide the physical memory into set of six size frames. On the other hand, the logical address space, you also divide it into blocks, and each block is, and all of them have the same size, and the size of the block is the same as the size of the block in the physical memory, right? And then you also number these blocks as you simply give them numbers or IDs like 0, 1, 2, 3, 4, 5, right? So page size, and each of this block is then referred to as page, and the page size is same as the frame size. Any questions that until this point before I go to the next slide? No. Okay. So what we do is like after we have yeah, what we do here is that after we have like divided our physical memory into frames, so now let's say that some frames are already occupied, right? And those frames which are already occupied, they are shown as in the blue color, and the one which are not yet occupied, they are shown in the white color here. Okay. So now let's say that we have this program, and we if we want to actually run this program, which has how many pages? 6 pages. So to run this program, we ideally, like in ideal situation, we will it is best that if we can find 6 empty frames in the physical memory, right? So we load these pages into uh, the physical memory. Okay. So here we are just mapping. So since this block was free, so we load the page 0 into the frame 1. So we simply keep a mapping, a record of the mapping that 0 is mapped to 1. Page 0 is mapped to frame 1. And then we load the next page into the next available frame. So which is 4. So we simply update our mapping that page 1 is mapped to frame 4. Then page 2 is mapped to frame 2. Then page 3 is mapped to frame 7. Then page 4 is mapped to frame 9. And page 5 is mapped to frame 6. So this mapping, which tells us that which particular page is mapped into which particular frame, this mapping is known as page table. So we can simply index the page table by using the ID of the page. So uh, we use the ID of the page to index the table, and it tells us then, okay, the number or ID of the frame in which it is loaded. Any question at this point? Is everyone clear of what the page table is and what is its job? It simply translates the that or it simply tells the information that where in in memory, in which particular frame of the physical memory a particular page of the page is loaded, page of a program. Okay. So here we have an example again to understand how page table is used. So this is your logical memory, or this is your logical address space. So your program is broken down into 4 pages, right? Page 0, page 1, page 2, page 3. Here we are not specifying what is the size of the page, but it is your program is like divided into 4 equal size blocks, and they are referred as page 0, page 1, page 2, and page 3. And then you have this page table, which is already populated. How it is populated? By loading pages into the frame. So as you load a page into the frame, you populate the table, right? So at this time, you have already populated the table. So by now, just by looking at the table, you can get the information that where a particular page is residing in the physical memory. So for example, if you want to look where the page 2 is residing, right? So you go to the table and index is using the ID of the page. So you look at the entry 2. When you look at the entry 2, its content is 3. So which is telling you that page 2 is loaded in frame 3 of the physical memory here. See, right? And again, for example, if you want to look where the page 0, let's say page 3 is loaded, you index the table using the page ID. So the page ID is 3, and you go to the entry indexed at 3 and read its content. The read of content of that entry is 7. So it is basically telling you that page 3 is loaded into frame 7 of the physical memory. Okay. So remember we said that the addresses that are generated by the CPU are the addresses that are generated by your program or process. They are actually the logical addresses. However, the addresses which are used for actually accessing the memory, they are the physical addresses. And then the question is that how we convert in the paging scheme, under the paging scheme, how we convert a logical address into the physical address. In last lecture, we talked about how we can convert it by adding a base value to each address, right? But that is when we are not using the paging, right? That is when you are using, for example, the contiguous allocation. Then you can use that base plus limit register approach, right? But here we are not using the contiguous allocation, right? For example, now under the contiguous allocation, what was the requirement? That these 4 pages should go to the physical memory in a contiguous chunk, like they should be next to each other. But that is not the case under paging. Under paging, page 0 is here, page 1 is here, page 2 here, page 3 here. They are not contiguous and they are not in order. You put the page in any free frame wherever you find it. Okay. Okay, so since they are not contiguous, so we cannot use that base plus limit approach to translate a logical address into the physical address. Then the question is that how physical logical address is converted into physical address under paging, right? So for that, what we do is that the address which is generated by your CPU is divided into two components, right? So the one component is known as page offset and the other is known as page number, right? What is page offset? So page offset is basically like, let's say if I'm saying that this page is, let's say, let me try to keep it simple. Let's say it is 10 bytes. 10, each page is of size 10 bytes, right? So, and let's say I want to, the address that I generated refers to the byte number 5 in page 0, right? So, how far it is, and when I say byte number 5, it's mean indexed at 5, like the first byte is index within the page is index 0. Let me go to the OneNote to explain it because I don't want you to be confused. Because the issue is that if you don't understand it clearly at this point, then in future you will be struggling with the idea of the paging. So let's say you have a page of a given size. And in this case, an example, I'm just assuming that each page is of size 10 bytes, right? Now, let's say that address that you any given address that that is generated by the CPU is pointing to a particular byte. Let's say you have like multiple pages of a process. Let's say 2 pages. The process the space requirement or the space memory space of the process consists of 2 pages, right? And both of them are 10 bytes with CSCI, right? Let's say this is page 0, this is page 1. So the address that is generated, it can be anywhere within these 2 bytes. Now let's say I assume that the address that is generated is within the page 0, right? Now how we can identify this particular byte by combining two pieces of information. The page number where that byte is located, page number, plus the offset within that page. Not plus, plus, let me put the comma not to confuse you, because we need two pieces of information. It doesn't mean that we are adding the addresses, okay? Yeah, just give me one. Okay. So the first piece of information is the page number where that byte is located. And second piece of information is where within that page that byte is located. So which is known as offset. So for example, if you say that it is located in the first page, so the page number is 0. Then the offset is how far from the start of that page it is located. So if it is the first byte in the page, the offset is 0, right? If the next byte, the offset is 1. If the next byte, like third byte, it is the offset is 2. So let's say this is our required byte. So the offset will be 2. So in order to refer or in order to access uh, memory location or a byte within a page, what we need we need two pieces of information, the page number and the offset within the page number where that byte is located, right? So that's why what we do is that any address that is generated by the CPU, we break it in two component, right? So that is broken down into two component. The first component holds the offset, and the second component holds the page number, right? So for example, again, let me say that you have a program uh, which is only 16 byte long. Like its memory requirement is 16 bytes, right? So I'm just writing here byte 0, byte 1, byte 2. Let me make it 8 because I don't want to write up to 16. Byte 5, byte 6, byte 7, right? And let's say uh, we say that page size is, we had the page size equal to 2, right? So then I simply break it 2, 2, 2, 2, right? So this is page 0, page 1, page 2, page 3, right? Now, if I have 8 bits, 8 memory locations are 8 bytes, how many address bits I need to address to identify each one of them? 2 raised to power 3 is 8, right? So I need 3 bits. So I need 3 address bits, A0, A1, A2, right? Now, how many pages I have? Page 0, page 1, page 2, page 3, right? How many pages? 4. How many bits I need to identify 4 pages? 2 raised to power 2 is equal to 4. So it's mean that out of these 3 address bits, 2 will be used to identify the pages. And the remaining, they will be used to identify the bit within a page, or these it will be used to specify the offset, right? For example, now you can give me any 3-bit address. Let's say you give me address 101, right? I will break it down 101, sorry. So this is basically telling me page number. So what is the page number? And then this is giving me the offset. What is offset? 1. So it is saying me, okay, this is the address in page 2, this page, and byte 1, offset 1, this one. So I am accessing this particular byte. Okay. Is everyone clear on this? How we are dividing the address into first thing is that we need two pieces of information to identify a memory location under paging scheme, the page number and the offset. And for that, we divide definitely our address into two components, page number and the offset. And how we know that how many bits will be used, how many bits of the address will be used for specifying the pages and how many bits will be used to specify the offset. It definitely depends upon what is size of your page and how many pages you have. Like for example, in this example, we had how many pages? Four pages. So 2 raised to power 2 is equal to 4. So 2 bits are used to specify the page number. And then how many bits we have in within a page? Only 2 bits, right? So 2 raised to power 1 is equal to 2. So we used only one bit to specify the offset here, right? If you have any confusion, let me know. Also, let me check the time. Now we have some minutes. Okay, so what we do is that let's assume that your logical address is consisted of m bits, just like in my example, our logical address was consisted of 3 bits. Then the total logical address space is 2 raised to power m bytes. Just like in our example, it was 2 raised to power 3 equal to 8 bytes, right? So we assume if we assume that the page size is 2 raised to power n bytes, like for example in our case the page size was what, only 2 bytes, which means that n was what, 1, right? So then we use n bits of the address to specify the page offset, and then whatever remaining bits we have, which basically mean m minus n bits, we use them to specify the page number. And the page offset bits, they are normally indicated by writing D, and the page number is bits are indicated by writing P. Is everyone clear on this one? How we divide an address into offset and page number? No question? Okay, so here is an example. M is 3 and N is 2. What does it mean? M is 3. M is 3 mean that total number of address bits are 3. So it's mean that how many memory locations we have? 2 raised to power 3 equal to 8. So logical address space is from all 0 to 7, right? And N is equal to 2 mean what? That how many bits we have, how many memory locations we have in one page? 2 raised to power 2, which is equal to 4, right? So in one page we have 4 memory locations, right? So it's mean that we simply divide our total memory space into two pages, because first page 0 covers first 4 locations, next page covers next 4 locations or 4 addresses. So now how we do the address translation, right? The underpaging from logical address to the physical address. Now the logical address, remember that the address which is created by CPU is the logical address. So we first divide that logical address into two components. The bits which are used to identify the page number and the bits which are used to identify the offset within a page, right? And then the page number which we have retrieved from the component of the address, logical address, we use that page number to index the page table. Like for example, if page number is 10, we will go to the entry number 10 of the page table and we read the content of that entry. And what will be the content of that entry? It will be a frame number, right? What is frame number? Just like uh, page number tells us, identifies the page, frame number will identify a frame in the physical memory, right? And then we combine the frame number with the offset bits coming from the logical address, and together F bits and the D bits together, they make the physical address, right? So again, we have an example in here. So let's say that we have page of size 4 bytes. So if each page is of size 4 bytes, how many bits we need in the address to specify the offset within the page? 2 raised to power 2. So we need only 2 bits, right? So if we have 4-bit logical address, 2 bits will be used to specify the offset, right? And the remaining bits, which mean 4 minus 2, the remaining 2 bits, they will be used to specify the page number, right? Now, let's say we have this logical memory or logical address space of a process ranging from 0 to 15, and the value at the logical address space 0 is A, at 1 we have stored B, at 2 we have C, and so on. So again, since we said that our page size is 4, so we have 4 pages: page 0, page 1, page 2, page 3, right? And suppose that we already this table is already populated, mean that these pages are already loaded into the frames. You can see on the right that you have physical memory and the pages are already loaded into the frames. So, and as a result, the page table is populated. Now, let's say that if now how we can convert the logical address 5 into the physical address. So if logical address is 5, what will be the physical address? For that, what we need to do? First, we need to convert 5 into the binary form and then break it into two components. What components? The page number and the offset. So when you convert it to the binary, it is 0101. Why we are converting it to the 4 bits? Because our address is 4-bit logical address, right? So we are generating a 4-bit binary of logical address 5. And again, what we said, the higher two significant bits, they will be used to identify the page number, and the least significant 2 bits are used to identify the offset. So the page number is what? 01, which is 2, right? Now you look, so this is 2. So you index the page table in that page number. So which is 2? So 2 is telling us that the frame number is 1, right? Here, the frame number is 1. Oh, sorry. This is not 2. This is binary of 1. Why are you not? Okay, I'm making mistake, but where is the eraser?
I see.
So
So we check page 1 then,
yeah,
and then
so we go to the, yeah, so it says frame number what? 6, right? 6, and then within 6, what is the offset? Offset
also
is
1.
1. So if you go to the frame number 6, okay, wait. So physical addresses, the frame number is 6 here, 1. Wait a minute, what's happening here? Am I reading it wrong? So 0101. So the page number is 1. Why it is converting into 3? It should not. Oh, okay. Yeah. So this is the frame number, right? 110. Okay. So the frame number is 3-bit address. Okay. Why? Because number of frames in the physical memory, they are not supposed to be the same. The total number of frames in the physical memory are not supposed to be the same as the total number of pages in the logical memory. So if, for example, if the total number of pages in the logical memory is only 4, then yes, you can have only 2 bits to specify the 4 pages. But there is no such restriction under paging that the number of total frames in the physical memory are the same as the total number of frame in the pages. Yes, the size of each frame is same as the size of the page, but the total number of frames are not required to be the same as the total number of pages. That's why if we have here, we are assuming that we have more than 4 pages. So for example, if you have in total more than 4 frames. So for example, if you have in total 8 frames, so you need to use at least 3 bits to identify them. So that's why we are using 3-bit value, 3 identify the frame. So the frame number is 6. So when you convert it to 3-bit binary, you get 110, right? And then remember that offset is same in the page in the logical address and the physical address. If I take you to the previous slide, so you simply copy over these D bits and uh, concatenate them with the frame bits, right? So here the offset bits are same. Okay. So it is actually the physical address is 11001, right? So which is equal to so it is basically saying frame number 6. So if you go to frame number sorry, it is basically giving you the address. Let me read. So what was the address? 5, right? E, yeah, here. So you can convert it into the frames. So you have like here you have frame 0, 1, 2, 3, 4, 5, and 6, right? So the frame number 6 and the offset is what? Offset is 1. So it points to uh, F here, right? So what was our logical address? Our logical address was 5. So 5 at 5 you have F here, and in the physical memory that page is loaded into the frame number 6, and the offset is same 2, just like here 1, just like here you had the offset of 1, here too you have the offset of 1, right? So this is how you convert a logical address into the physical address. Let's do another example. Let me check the time. Yeah, I think let me finish at least this slide. So let's say now we have logical address 11. So how can we convert it into the physical address? Exactly same procedure. So first, what you need to do is that need to convert this into the binary form and then break it into the page number and the offset. So when you convert into the binary, you get 1011. So these first 2 bits give you the uh, page number. So page number here now is 2, right? So you look into the table and index it using the page ID. So when you look at entry 2, it is giving you the frame number 1, right? So what you do is that you replace the page number with the 3-bit uh, binary of the frame number. So it is 001 because we had frame number 1. So when you convert it 3-bit binary, it is 001, and your offset remains same, which is 3, right? So you look into the frame number 1, which is this one here, right? And you then follow an offset of 3. So which is 0, 1, 2, 3. So you are reaching I, right? What was the address? In logical address space, it was 11. So if you look at address 11, it is 1. Okay. It is I, not 1. So the I is stored at logical address 11, and I is also stored at physical address 7, which is equivalent of frame 1 and offset 3. One more example, and I think we are done with this slide. How to convert the logical address 13 into the physical address. Again, same thing. You first convert into the binary, which is 1101. So then you break the address into 2 components. The first higher bits give you depending upon your addressing scheme. But in this example, we are, since as we said, we have in total only 4 bits address bits, and we have the page size of 4 bytes. So 2 bits are used to specify the offsets and 2 bits to specify the page number. So here we are getting the page number 3, and offset is 1, right? Again, you refer the table. The table tells you that frame number is 2. So what you do is that you replace, you put here the 3-bit binary of 2, which is 0, 1, 0, right? And the offset remains the same as in the logical address, right? So here your frame number is 2, frame number 2, this one here, and follow an offset of 1. So you reach n, right? And you can also confirm it that it is the address, logical address of that data is 13 by just looking at here in the logical address space. Okay. So logical address and physical address, they have the same data, but addresses are different. And again, keep in mind, logical address is not something which refers to actual physical memory. They are only for uh, giving an illusion to each process that whole address space is allocated to them, while actually it is not. Please, can you kindly make today class and last class available on YouTube before the end of today? Just be clear, everything on paging will not be on the exam, but the other topics covered will be on the finals. Okay, to the last question, yes. Whatever we covered today, starting from paging, it will not be appear on exam. Okay, so you are not responsible for that. Responding to the first question, yeah, I will make the videos available for previous lecture and this lecture. I will provide the link on the syllabus page. Okay, anything else? No? Okay, so if not, then good luck for the exam. And as I said, tomorrow I will release, on Friday, I will release the practice exam with the solution. So try solving it and not responsible for anything other than the last lecture, which is covered, which is today. Okay.
And just making sure
So
we can have like a piece of printer paper front and back for it.
yeah. It like you can have an A4 page, it can be handwritten or it can be printed, doesn't matter. It doesn't make a difference. Okay, Rupak, you have a question about the project.
Hi. Yes. So I sent an email to you yesterday. So I was working on project for module B.
Okay,
Thing that I noticed, I ran the code on CS machine. The
okay.
output that I'm getting is not the same output the one that you provided. So do you want us to match the output? So I was able to match the output by using sleep statements in both producer and consumer functions, like towards the end of the function.
And producer and consumer. Okay, I will reply via your email because I need to first look into your code. Have you added your code, attached your code to the emails?
Not yet. I can send it to you.
Okay, then attach and I will have a look at it and then respond to you.
Okay, sounds good. Thank you.
Okay. Anything else? No? Okay, then good luck and hopefully I will be there by next semester and see you there.
Hmm.
Bye.
Thank you.
Bye for now.
Thank
Thank
you.
you. You too. Have a good day.